Hey everybody. So today we're going to start taking a look at applications with log functions, which is really just word problems. Everyone's favorite thing in the whole world. But the advantage is, walking into the stuff that we're going to be covering for the next few days, you actually already know the algebraic process to use to solve it. It's just going to be a matter of applying that algebraic process to solve each one of these application problems. Now, some of them are going to be really simple, straightforward formulas that we've been doing for weeks or a month. Others of them, we may give you kind of a novel formula. So the fun part about this is there's lots of different ways that we can incorporate logarithms and natural logarithms to solving certain types of exponential functions or other applications, right? So instead of a more traditional kind of notes day, what we're going to end up doing today is just taking a look at a few examples that are actually from the assignments that you guys are supposed to be doing today. Because like I said, we're not really learning anything new, but what we are doing is we're learning and we're training our brains to be able to apply the mathematical facts that we already know to novel and new types of problems. All right. So first we're going to go through and take a look at two examples from worksheet 1. So we're going to look at number 3 and number 6, so kind of the middle and the end of it. So we're going to work our way through each one of these. Okay. So if you guys want to go ahead and take out the assignment and work along with, that would be great. I'd suggest you do it on your own sheet of paper. Obviously, I've got a lot more space on mine than you guys will have on your single sheet printout with 6 or 7 problems on it. So let's go ahead and take a look at number 3 from worksheet 1. It says that you purchased a plot of land for $45,000. The value of the land increases by approximately 5% each year. How long will it take for the value of the land to double? So before we start trying to go through and immediately start working, I'm going to take a highlighter and go and I'm going to highlight what I think all of the important values are. Okay, so I know that I purchased something for $45,000. Okay, I know that it is increasing in value by 5% each year. So we should have a rough idea of what formulas we should be using because that terminology looks very familiar. The interesting part, though, and what's new here, is that the question is, how long will it take? Okay, we haven't really answered that type of question before. How long will it take for the value of the land to double? All right, so what we need to think about is what formula would be appropriate for me to use here. Okay, well, obviously it's saying that we start off with a value and it's increasing, so it's got to be some sort of growth. It's increasing by a percentage every year, so that tells me that I'm going to need to use the formula A equals P times 1 plus R to the T, okay? Because that's my general form for exponential growth, especially if it's happening yearly, okay? So what are all the values in here that I know? Well, I've got A, I've got P, I've got R, I've got T. So what are each one of these? Well, A is the final amount. Do you know what the final amount is? Not exactly, but you could figure it out really easily because it's saying how long will it take for the value of the land to double? Well, double from what? The $45,000 that you paid for it, right? So the final amount is just 2 times 45,000, which is simply 90,000. Okay? So double 45,000, 90,000, makes sense? Okay, P was your principal or the starting amount. Well, how much was it worth at the very beginning? Well, just $45,000. Okay? At what rate is it increasing? 5%. But we got to remember that we always express those percents as decimals, so that's going to be 0.05. And T is time. Well, isn't that what I'm trying to find? How long will it take? Isn't that measuring time? So this is actually the variable that we're trying to go through and solve for in the problem. So, hopefully you can see why this is in the applications with logs, okay? Because if I go and start plugging all of this in to the formula, then I'm going to have 90,000 equals 45,000 times 1 plus 0.05 raised to the t. So the variable that I'm trying to solve for is t, and that's in the exponent, hence why I'm going to need to use a log. So I need to go through and isolate my exponential base so that I can take either the common or natural log of each side. All right, so the first thing I'm going to do is I'm going to divide both sides by 45,000. Well, coincidentally, if I divide this by 45,000, it reduces just to 1. If I divide this by 45,000, I get 2. So it doubled. Okay, so I have 2 equals 1.05. I went ahead and just added 1 plus 0.05, 1.05, okay, raised to the t. Okay, so divide by the 45,000 on both sides, combine what's inside the parentheses, okay, and then I can go and just take the common log or the natural log of each side. I'm going to go ahead and just choose to take the common log of each side. So the common log of 2 will equal the common log of 1.05 to the t. But then properties of logs tell me that I won't have an exponent, it's actually a coefficient, so I get the common log of 2 equals t times the common log of 1.05. So now I can go and just take my calculator here and do a little division. So I'm going to hit common log of 2, and I'm going to divide that by the common log of 1.05. Okay, so I've got all that in my calculator. I hit enter, so it gives me 14.206. So let's just go ahead and round to 2 decimal places. So I end up getting 14.21 equals t. All right, so what's that telling me? Well, that's helping me to answer the question, okay? How long will it take for the value of the land to double? It will take approximately 14.21 years. We got to keep the units consistent. So 14.21 years for the value of the land to double if it is increasing in value by 5% each year. All right? So again, once we go and we have the equation written like this, it's exactly like solving exponential equations with unlike bases. We just had to go and recognize that this would apply to a formula, that we were given certain variables, and now we're finding for an exponential term instead of what we were doing before, where we were always asking how much is the land worth in 12 years if it increases at whatever percent interest. Okay, so this isn't anything new that we've learned. We're just applying all of the things about logarithms and exponential equations that we've already learned. All right, so let's go take a look at number 6 on that same page. All right, so this one's a little bit more straightforward. It says you deposit $975 in an account that compounds interest continuously. After 5 years, the value of the account is $1,132.79. What percent interest was the account paying? All right, so again, this is a word problem. If we're going to go and solve, we need to have some sort of equation to solve, and that equation is probably coming from one of our formulas. So what are the important values here? Your original deposit of $975, okay? Because that's giving you your principal, your starting amount. You also know that it's compounding interest continuously. That tells you that you're going to be using that PERT formula, okay? P times E raised to the RT, all right? It also tells you that after 5 years, so you have the value for T, the account is worth $1,132.79. So what are you trying to find? You're trying to find the interest rate, all right? So thinking along the same lines that we did for the last problem, we need to go and identify that we're trying to use a formula. So A equals P times E raised to the RT. Okay? We know that it's the PERT formula because it has the word continuously with how it's compounding interest. Okay? So what are all of the different variable expressions we have in this? We have A, we have P, E is the natural number E, it's not a variable. Okay? R is the interest rate, T is the amount of time. So the final amount that the account is worth was $1,132.79. The principal was $975. The interest rate is what we don't know, so that's our variable that we're solving for here. And T was 5 because it's 5 years. Okay? And remember, every time we're looking at these money formulas, we're always measuring time in years. All right? So if I go and I plug all of those into the equation, I'm going to get 1,132.79 equals 975 times E raised to the 5R. You could also say R times 5. I just like to write it as 5R because habits are hard to break. Okay? So now if I'm going to go and solve this, I'll go through and show my steps a little bit more this time. So first, I know that I'm trying to solve for R. R is in the exponents. It's the exponent of a base of E. So I got to get E by itself. So I'm going to divide both sides by 975. Okay? I can either leave it as this ratio, or I could go through and approximate it using my calculator. So I'm going to go and say 1,132.79 divided by 975. That gives me this. But you see how I have this very long string of decimals? The more of those decimals I include, the more accurate my answer is. So I'm going to go ahead and write down all of them. Okay? So this has now turned into 1.161835897. Okay? Like I said, it might have been easier had I just left it as this ratio in my calculator, but I'm just going to go ahead and write it this way. So that will equal E raised to the 5R. So I've gotten my exponential base all by itself. What I need to do now is take the natural log of each side. Why am I intentionally choosing the natural log? Because I have a base of E. So I'm going to go and take the natural log of this 1.161835897, okay? And that's going to be set equal to the natural log of E to the 5R. Well, anytime that I have the natural log of E, that's really just an inverse operation, so that just kind of disappears off the face of the planet. So I'm left with the natural log of your 1.161835897, and that will equal 5R. So then some basic division will go through and tell me what my solution will be. Okay, that's obviously a number that I want to go through and do in my calculator. The advantage is I've actually left that number in my calculator, so I don't have to go and retype it all in again. What I can do is I can just hit the natural log button, okay, but I can hit second and the minus sign, and that just pulls up answer, which is the last answer that you came up with on your calculator. All right, so I'm going to go the natural log of that value, which is right here. Okay, close my parentheses, very important. Divide that by 5, and you end up with this number, 0.030000. Okay, so 0.03, and I could keep going, but I've got what, 1, 2, 3, 4 zeros down the line, which aren't really going to count too much for all of this. So I'm just going to say 0.03 is equal to R. So converting that into an actual percentage, your interest rate would have been 3%. Okay? Now, How come it wasn't exactly 0.03? Again, we've got a lot of rounding. When we're talking about dollars and cents, it only goes to cents. We don't ever talk about, tenths of a penny, okay? It just goes into that amount. So the more rounding that you have, the more inaccurate your answer could be. That's also why I didn't want to go and just write this as, 1.16, because if you just did the natural log of 1.16 and then divided that by 5, you get a number that's a little bit less than 3%, and when you're comparing like 2.9% to 3%, that could be a big deal, all right? So, like I mentioned earlier, the more decimal places we follow to, the more accurate our solution is going to be, all right? So, now let's flip it over and take a look at the second worksheet, okay? So, the one at the top looks like it's a doozy. It really isn't that bad at all, okay? So, again, now we're on worksheet 2, and we're going to take a look at these two problems. So the first one says, the loudness of sound, D, measured in decibels, is given by the formula D, or the decibels, equals 10 times the common log of I over 10 to the negative 16th, where I is the intensity measured in watts per square centimeter. The denominator, which is 10 to the negative 16th, is the approximate intensity of the least sound audible to the human ear. So the quietest it can be is that 10 to the negative 16th, okay? So, our question here says, if a normal conversation is held at an intensity of 3.16 times 10 to the negative 10th watts per square centimeter, how many decibels is this, okay? So, we've got an equation, we have some values, and we're trying to find how many decibels it is. So, again, this is just a novel equation that we're using to answer something. All right, so the equation that we have is that D equals 10 times the common log of I over 10 to the negative 16th, okay? So what values have we been given? We're trying to find D, okay? We're trying to find how many decibels is this. So that's what we're trying to find. Were we given the intensity of a normal conversation? Yeah, it's right there, okay? So I've been given that value. I'm trying to find this value, and the rest of it is just logarithms. So let's just go through and plug some of that stuff in. So we know in this problem that I, the intensity of a normal conversation, is 3.16 times 10 to the negative 10th. Okay, we're just going to leave it like that. I'm not going to ask you guys to go and write like 9 zeros in front of that. I'll show you how to do that on the calculator. It's a whole lot easier and less typing. Okay, and we're ultimately trying to find what D is. Those are the only two variables in that equation. All right, so let's go through and plug it in. So D will be equal to 10 times the common log of the intensity of a normal conversation is 3.16 times 10 to the negative 10th, and all of that is going to be over 10 to the negative 16th. Now, at this point, if you're wondering, hey, couldn't I go through and do an expansion because I've got a division inside of a log problem? Absolutely, you could do that. But the advantage is here, we don't really have to. We can just do a good old-fashioned plug and chug. So, if we go and take our calculator, okay, I'm going to go ahead and clear it out, but because we're solving for D and everything else is over here, it's time just to start plugging stuff in. So, we're going to say 10 times the common log of, and in a separate set of parentheses, so make sure you got 2 right there, I'm literally going to type in 3.16 times 10 raised to the negative 10th. That's a whole lot less typing than 0.00000000316. Okay? Close the parentheses. So that's my numerator. Okay? I'm going to go and divide that by, put it in its own set of parentheses, this 10 to the negative 16th. So 10 raised to the negative 16th. Put the denominator in a set of parentheses and close the parentheses around the logarithm. Okay? So hit enter, and it gets me 64.9968. So D equals, in this case, 64.99. So about how many decibels is that? Well, if I was a bet man, I would say that D is approximately 65 decibels. All right, so log function, or at least a function with a logarithm in it, given certain values, get the equation down, identify what all the possible inputs are, figure out which one you're solving for, and then just move forward with the problem. Okay? So, on that same worksheet, we'll go take a look at number 3 now, which again is one that looks like it's a whole lot different, but it's actually not bad at all. So it says a satellite has a radioisotope power supply. The power output in watts is given by the equation P equals 50 times E raised to the negative T over 250, where T is the time in days since the power supply was placed in service. So we got 2 questions to answer. A, how much power will be available at the end of 1 year? And B, the equipment aboard the satellite requires 10 watts of power to operate properly. What is the operational life of the satellite? Okay, for those of you looking for context, basically it says this satellite has a battery. But as we all know, over time, batteries lose their electrical charge. That charge is measured in watts. Once the electrical charge is below 10 watts, the satellite is no longer going to function properly. So what we're trying to do is figure out how much juice is left in the battery after a year, and how long will that battery keep the satellite up in orbit. Okay, so we're going to split this into a part A and a part B. Okay, so we'll do A over here, we'll do B over there. So we have our function, which is P equals 50 times E raised to the negative T over 250. Okay, so how much power will be available at the end of 1 year? Okay, well, P is power, right? So that's what we're trying to solve for. Okay, E is the natural number. It's not a variable, but I do know what T is. Okay, T in this case is 1 year. All right, so I can go and I can plug these 2 things in. I can say that the power available in the satellite after 1 year will be equivalent to 50 times E raised to the negative 1 divided by 250. So that's just going to be a plug it in the calculator kind of problem, am I right? So we're going to go and hit 50. The E is the secondary function of your natural log, so times E raised to the negative 1 over 250. Okay, hit enter. So how many watts are left in the battery, or how much power is left? Well, 49.8 watts. Okay, except for, what did we forget? Remember how we always go through and highlight stuff? It's always a good idea to highlight stuff. So the power output in watts is given by this equation, where T is time in days. How many days are in 1 year? 365. Aha. So we don't want to say 1 year, we want to say 365 days. So is this value really negative 1? No. It's going to be 365. So the power available to the satellite after 365 days is going to be 50 times E raised to the negative 365 over 250. My apologies to those of you that are cursing, but I was hoping that we would have gone through and read everything, and you would have called me out before we got to this point. If not, it's all good. We're here now. So we're going to go through and say it's 50 times E raised to the negative 365 over 250, and we're going to come up with 11.61. Okay, so the power that is available after 1 year is 11.61, and since power is given in watts, we're going to express it as watts. Okay, so can this particular satellite operate for a year? Absolutely. Okay, now we can move on to part B, where it says the equipment aboard the satellite requires 10 watts of power to operate properly. What is the operational life of the satellite? Well, in order to do that, we're really using the exact same formula, right? Where P equals 50 times E raised to the negative T divided by 250, okay? But if the power dips below 10 watts, it doesn't work anymore, okay? So in this case, I've got variables where I have P and I have T still, okay? But P has to be 10, okay? Because if it's below 10 watts, it doesn't work anymore. T is really what's going to be my variable, my question that I'm solving. All right, so let's go and plug those in. So we're going to say 10 equals 50 times E raised to the negative T over 250. All right, so we're solving for T in this problem. So first I need to go through and divide both sides by 50. So that's going to give me 1/5, which I just so happen to know is 0.2. So 0.2 will equal E raised to the negative T over 250. If I'm going to solve this, I need to take the natural log of each side. Why am I specifically choosing the natural log? Because I got a base of E. So the natural log of 0.2 equals the natural log of E raised to the negative T over 250. Well, the natural log of E is an inverse operation, so those just wipe each other out. So we end up with the natural log of 0.2 equals negative T over 250. Well, how do I get rid of that denominator of 250? Multiply both sides by 250. So 250 times the natural log of 0.2 will equal negative T. If I multiply each side by negative 1, then I could get a negative 250 times the natural log of 0.2 will equal positive T. So let's go and plug that into the calculator. So negative 250 times the natural log of 0.2. And that gives me 402.359. So let's just go ahead and say that T is 402 we'll call it 36. So 402.36 equals T. So what is the effective lifespan of the satellite? About 402 days, and then a couple of hours. So whether you went through and said approximately 402 days, approximately 402.36 days, or if you went through and said, well, that's about a third, and a third of the day is about 8 hours, so about 402 days and 8 hours, I'm okay with any of those solutions, okay? But the big takeaway that I want you guys to have from these 4 problems is that you already know how to do the math. It's just up to you to figure out where that math needs to be done. So you've got a handful more problems to go through and do, but try and knock those out as best you can. And if you have any questions, please make sure you stop by office hours.